All right, let's do some more practice with Newton's laws. Again, our first two Newton's laws. The one we're going to focus today would be the second law. The sum of the forces equals the mass times acceleration. And here are my steps in solving force problems. The first step is what forces are acting on our object. Draw a free body diagram for each object. Select your coordinate system. Break all your forces into their x and y components, and then apply Newton's second law. Generally, there will be two directions you can do that in. You may not always need them, but there are two. And then solve for what you need. So our first problem is a problem here. So how long will it take this block of mass 3 kilograms to reach the bottom of this frictionless incline starting from rest? So we look at this problem and we know that there's 3 meters distance there. If we can find the acceleration that it has, it starts from rest. It's a pretty easy kinematic equation then to figure out exactly how long it'll take to do this. So let's look at this here and set up our free body diagram as discussed, and start off with what forces are acting on our object. So our object is the block, and so we want to draw our free body diagram. So take a second and think about what forces are acting on this block, maybe even try to draw the free body diagram, and then we'll go through. Okay, so what forces act on the block? There's the weight due to gravity, mg, which is straight down, and then the normal force, which is going to be, as usual, perpendicular to the surface. Now, there could have been friction, but we're told in this problem that it was frictionless. So it's like an ice surface of this incline or whatever. And so we can neglect friction for this part here. So this would be our first two steps. We've drawn a free body diagram, and we've figured out what our forces are. So now our coordinate system. It's almost always, not always, but almost always going to be advantageous for us to use a rotated x and y coordinate system so that the x is in the plane of the incline. And so if we break our forces, or look at our forces, our normal force is already in the positive y direction. So that one's fine, that's all good. Our mg, however, needs to be broken into its x and y coordinates. And so the way we do that is something like this here. So we did this kind of stuff when we were talking about vectors. The important parts here is that whenever you break the vector down, okay, the x and the y components should make an angle of 90 degrees with each other, and the original force, the mg, should be the hypotenuse of your triangle. And so if you look here, hopefully you can see that this angle, I'll call it phi, is the same as that angle, which what that implies is that this angle over here is the 30 degrees. And so then when writing these out, I can say that my mgx, the component of the weight in the x direction, is mg sine 30, and the component in the y direction is mg cosine 30. So stop for a second and make sure this all makes sense to you. This is a pretty key piece of these types of problems. The good news is that it'll generally you can always sort of work it out this way, as long as this is the angle down here. That's the one that you're given. And so I usually like to actually then split it up like this here. And so now I've got 3 forces. I took one and split it up just to make it easier to understand. And so we applied Newton's second law. So the acceleration will be down the incline. And so if you look in the y direction, I got something like this. The normal force equals mg cosine 30 equals 0, because again there is no y acceleration. Our coordinate system was this one where y is this way and x is this way. So the acceleration is all on the x, which leads us to this situation here where the normal force is mg cosine of 30. Again, this is going to be a common thing that we'll find as long as this is the angle that we're given. And so one thing just to note, the normal force only equals part of the weight of the block. So because it's inclined, it only holds up part of the weight, and the other part of the weight is what's going to account for the acceleration. And so if I do this then in the x direction, I get mg sine 30 equals ma, and what's nice is the mass cancels out. And we get ay equals g sine of 30. A couple comments on that. So acceleration is less than g, which makes sense, right? This shouldn't have just the gravitational acceleration. One thing you can do too in a case like this with inclines is take basically any of these answers, but this is a good one to do here, and just imagine, okay, imagine if this 30 was 90 degrees, right? So sort of the extreme case where your incline, was like super high, so it's almost exactly 90 degrees or something, right? And so sine of 90 is 1, and you actually get g. So the extreme case where basically you are in free fall, you get g from this answer. And then furthermore, if you make your angle 0, okay, so it's just a flat surface, then sine of 0 is 0, and there is no acceleration. So you can always kind of take the two extreme cases to sort of help your reasoning, especially if you're kind of stuck with angles or something like that. And so now we go back to our problem. It wanted us to find the time it takes to slide down that incline, where there was a distance of 3 meters. And so what we do is we set up our if you remember, the incline was kind of like this here, and the box was here, and they told us that this distance was 3 meters. And so this is the same distance that the acceleration is, parallel to. And so we can just call this we're going to only do our motion in the x direction. We pull out our old faithful equation here, and this is called where it starts at 0, where it ends up at 3. And then we got this. Our acceleration, when I plug in g sine 30, is 4.905. And so I can go through and find that time final. And so it takes 1.11 seconds for this thing to slide down the incline. Okay, so now we got the same problem, but with friction. So we're going to assume that the block starts from rest and starts sliding. So we're going to deal with kinetic friction to make it a little bit easier. We want to go through and find what the acceleration is now. So we got what it was without friction. Now we want to see what it is with friction. So same steps. And what's nice is once you get used to sort of doing these incline problems, sort of adding a little extra piece like this is not hopefully too bad. And so what forces act on the block? What was our good old friend, those two forces before, the normal force and the weight due to gravity. And now we're going to have the kinetic friction, again, opposing our motion. So same coordinate system. What's nice is we've already broken those mg's into their x and y components, and so we're essentially just adding a frictional force. So here's how I would draw the picture. Once you break everything into its components, everything is in either the x or the y direction. Again, just to reiterate, this is the sort of rotated x and y axis. And so apply Newton's second law in the y direction. So last time we did it, we didn't really use it. We're going to use it this time, but it's the same thing. The same two forces. Friction doesn't affect this one. The normal force is mg. Again, the normal force only equals part of the weight of the block. Now, in the x direction, we've got two forces. So mg sine theta is in the positive x direction. So again, our typical xy axis. So this is the positive force, this is the negative force, equals ma. Now, you recall that the force of friction equals the coefficient of kinetic friction times our normal force. And so that would be our equation there. And so down here we've written that out. And so here we've got something that's a little bit different than we can have sometimes, which is that this normal force, again, doesn't equal mg, it equals a part of mg. And so we get mu k mg cosine 30. And so that is the force of friction. So we plug that in, and what's nice is there's a mass in every piece. And so we get that the acceleration in the x direction is g sine theta minus mu k g cosine theta. This term is going to decrease the acceleration, which is what we expect. When I plugged in the values here in this problem, I got 2.35 meters per second squared. And so these are the building blocks of these types of problems. And so physics books love inclined planes. But if you sort of have the building blocks dealing with the mg, dealing with the friction, then you can do a lot of different things and have a lot of flexibility with that. So two key examples. Also, if you haven't thought much about friction, make sure to go back and see the other video that's being released this time, which is dealing directly with friction. That should help out a lot.